this video, we'll be looking at the capacitors in circuits section. Now, when considering any components like a capacitor or a resistor in a circuit, we need to consider whether or not it's positioned in series or parallel. Much like with resistors, it has a huge effect as to which position we are placing it in. So let's consider parallel first. So here we have a fairly simple parallel circuit. At the top we've got the basic cell. Then we have two parallel branches with capacitors on each. Now, what we do with this is that we can understand that in a basic parallel circuit, the potential difference across each level, across each branch, will be the same as the potential difference provided by the supply. So whatever the voltage of the cell is in this case, will be the same voltage that will build up across the capacitor on the first branch and the second branch and any subsequent branches that you decide to add. As such, we can use a little bit of maths to derive a basic equation here for capacitance in parallel. First, consider the charge. Now, the total charge in this circuit will be equal to the total charge collected across each of the capacitors. So a simple sum of Q1, 2, 3, etc. for each capacitor that's positioned in parallel. As we know, Q equals CV, rearranging our basic capacitance equation. As such, it's possible to say that this total charge is going to equal the sum of C times V for each of the capacitors. So C1 V1, C2 V2, etc. added up. Now, this allows us a little simple trick because we know that V, the potential difference, is the same in V1, 2, 3, etc. So we can get rid of them. And this simplifies the equation to tell us that the capacitance is simply a sum of the capacitance of each capacitor placed in parallel. Now, this should look familiar because this is very similar to the structure that we had for the resistance of resistors placed in series. So we have an opposite situation here. What's true for resistance in series is true for capacitance in parallel. So let's see if that carries over for capacitors in series. Now, again, we need to draw a simple circuit diagram, starting with our cell at the top, and we're going to place two capacitors in series with each other. Now, again, we can use a little bit of mathematical logic, a bit of Kirchhoff's laws being played here, because we know that the potential difference of the supply will be shared across all components that are positioned in the series circuit. So V equals V1 plus V2 in this case. As such, we can again use the basic capacitance equation. So we know that V is equal to Q over C. Therefore, it's pretty easy to understand that Q over C for the whole of the series setup is going to be equal to Q1 over C1 plus Q2 over C2, etc. continued for as many as you have positioned in series. Now, we know that the charge will be equal throughout this circuit. It'll be the same charge built up on each plate as we go around. As such, we can get rid of Q. So we can see that 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3, etc. And yet again, we can see this follows the same opposite pattern as this was the equation we had for resistors in parallel. Thank you for your time.